Now, we're gonna discuss about the lesson 4, the nano world. The objective of this lesson is to define nanotechnology, characterize nanotechnology or the nanoscale, describe the various uses of nanotechnology, discuss concern on the use of nanotechnology, and explain the status of the use of nanotechnology in the Philippines. Scientific researchers have developed new technological tools that greatly improve different aspects of our lives. The use of nanoscale is one important interdisciplinary area generated by advancement in science and technology. Science and engineers were able to build materials with innovative properties as they manipulate nanomaterials. Indeed, research and application of knowledge on nanomaterials will continue to bring widespread implication in various areas of the society, especially healthcare, environment, energy, food, water, and agriculture. Nanotechnology refers to the science, engineer, and technology conducted to the nanoscale, which is about 1 to 100 nanometer or NNI 2017. Nanoscience and nanotechnology employs the study and application of exceptionally small things in other areas of science including material science, engineering, physics, biology, and chemistry. The concept of nanotechnology and nanoscience started in December 29, 1959 when physicist Richard Feynman discussed a method in which science can direct and control individual atoms and molecules in his talk, "There's Plenty of Room at the Bottom." During the American Physical Society meeting at the California Institute of Technology, the term nanotechnology was coined by Professor Norio Taniguchi a decade after the dawn of the use of ultra-precision machining, NNI 2017. How small is a nanoscale? A nanometer is a billionth of a meter or 10 raised to the power of -9 of a meter. The illustration shows how small nanoscale is compared to other particles or materials.
How to view nanomaterials. Scientists use a special type of microscope to view minute nanomaterial during the early 1930s. Scientists use electron microscopes or field of microscope to look at the nanoscale. The scanning tunneling microscope and atomic force microscope are just among the modern and remarkable advancement in microscopy.
Electron microscope. German engineers Ernst Raska and Max Knoll built the first electron microscope during the 1930s. This type of microscope utilized a particle beam of electrons to light up a specimen and develop a well-magnified image. Electron microscopes produce higher and better resolution than older microscopes because they can magnify objects up to 1,000,000 times, while conventional light microscope can magnify objects up to 1,500 times only. Scanning electron microscope or SEM and transmission electron microscope or TEM are the two general types of the electron microscope.
Atomic force microscope. It was developed by Gerd Binig, Calvin Quate, and Christoph Gerber in 1986. It makes use of a mechanical probe that gathers information from the surface of a material.
Number 3. Scanning tunneling microscope. This special type of microscopes enable scientists to view and manipulate nanoscale particles, atoms, and small molecules. In 1986, Gerd Binin and Heinrich Rohrer won the Nobel Prize in Physics because of this invention.
Nano manufacturing. It refers to scaled up, reliable, and cost-effective manufacturing of nanoscale materials, structures, devices, and systems. It also involves research, improvement, and incorporation of process of the construction of the material. Therefore, nano manufacturing leads to the development of a new products and improved materials. Two fundamental approaches to nano manufacturing. First is the bottom-up fabrication. It manufactures products by building them up from atomic and molecular scale components. However, this method can be time-consuming. Scientists and engineers are still in search for effective ways of putting up together molecular components that self-assemble and from the bottom up organized structures. The second approach is a top-down fabrication. It trims down large pieces of materials into nanoscale. This process needs larger amounts of materials and discard excess raw materials.
These are new approaches to the assembly of nanomaterials based from the application of principles in top-down and bottom-up fabrication. This includes deep pen lithography. It is a method in which the tip of an atomic force microscope is dipped into a chemical fluid and then utilized to write on a surface, like old-fashioned ink pen onto paper. Self-assembly. It depicts an approach wherein a set of components joined together to mold an organized structure in the absence of an outside direction. Chemical vapor deposition. It is a procedure wherein chemicals act in response to form very pure and high-performance films. Nano-imprint lithography. It is a method of generating nanoscale attributes by stamping or printing them onto a surface. Molecular beam epitaxy. It is one manner for depositing extremely controlled thin films. Roll-to-roll processing. It is a high-volume practice for constructing nanoscale device on a roll of ultra-thin plastic or metal. Atomic layer epitaxy. It is a means for laying down one atom thick layers on a surface.
Distinct features of nanoscale. Nanotechnology involves operating at the very small dimension, and it allows scientists to make use of the exceptional optical, chemical, physical, mechanical, and biological qualities of materials of the small scale. The following are distinct features of nanoscale. 1. Scale at which mass biology occurs. Various activities of the cell take place at the nanoscale. The DNA serves as the genetic materials of the cell, and it only about 2 nanometers in diameter. Furthermore, the hemoglobin that transport oxygen to the tissue throughout the body is 5.5 nanometers in diameter. A good number of modern researchers focus on advancing procedure, therapies, tools, treatments, and more, occurs and custom-made than traditional methods and cause no adverse effect on the body. An example of this is the biobarcode assay, which is a very inexpensive approach of identification of specific disease marked in the blood despite their small numbers in a particular specimen. 2. Scale at which quantum effect dominate properties of materials. Particles with dimension of 1 to 100 nanometers have properties that are significantly discrete from particles of bigger dimension. Quantum effect direct the behavior and properties of particles in this size scale. The properties materials are highly dependent on their size. Among the essential properties of nanoscale that change as a function of size include chemical reactivity, fluorescence, magnetic, permeability, melting point, and electrical conductivity. One example is the nanoscale gold, which is not only yellow colored element we are used to seeing, but it can also appear red or purple. Gold electrons display restricted motion of nanoscale, particularly nanoscale gold particles, selectively build up in tumors where they permit both precise imaging and targeted laser destruction of the tumor while avoiding damage on healthy cells. 3. Nanoscale materials have far larger surface areas than similar masses of larger scale materials. As we increase the surface area per mass of the particular materials, the greater amount of the materials comes in the contact with another materials and can affect its relatively. If 1 cubic centimeter is filled with micrometer size cubes, a tribillion of each with a surface area 6 square micrometers, the total surface area amount to 6 square meters, or about the area of the main bathroom in an average house. When the single cubic centimeter of volume is filled with 1 nanometer size cube of them, each with the area of 6 square nanometers, there are total surface area comes to 6,000 square meters.
Government funding for nanotechnology in different countries varied in 2005. First, the U.S. National Nanotechnology Initiative. The best known and most funded program is the National Nanotechnology Initiative of the United States. The NNI was established in 2001 to coordinate U.S. federal nanotechnology R&D. The NNI budget in 2008 and 2009 were $1.4 billion and $1.5 billion respectively. Number 2. European Commission. In February 2008, the ESC officially launched the European Nanoelectronics Initiative Advisory Council, or known as ENIAC. Number 3. Japan Nanotechnology Research Institute under the National Institute for Advanced Industrial Science and Technology, or the AIST. 4. Taiwan. Taiwan National Science and Technology Program for Nanoscience and Nanotechnology. Number 5. India. Nanotechnology Research and Education Foundation. 6. China, National Center of Nanoscience and Technology. 7. Israel, Israel National Nanotechnology Initiative. Number 8. Australia, Australian Office of Nanotechnology. Number 9. Canada, National Institute for Nanotechnology, or also known NINT. 10. South Korea, Korea National Nanotechnology Initiative. 11. Thailand, National Nanotechnology Center of, or NANOTEC. 12. Malaysia, National Malaysia Nanotechnology Initiatives, or also known as NNI.
Possible applications of nanotechnology in the Philippines. 1. ICT and semiconductors. 2. Health and medicine. 3. Energy. 4. Food and agriculture. 5. Environment.
Benefits and concern using nanotechnology. Nanotechnology has a various application in different sectors of the society and environment. Salamanca Buentelio proposed an initiative called Addressing Global Challenging Using the Nanotechnology to accelerate the use of nanotechnology to address critical sustainable development challenge. They suggest the model that could help figure out the possible contributions of the community in overcoming global challenges that pose risk on health and the other aspect of people. However, they are concerned that need to be addressed before using and promoting materials derived from nanotechnology, Diary 2005. Number 1, nanotechnology is not a single technology. It may become pervasive. Number 2, nanotechnology seeks to develop new materials with a specific property. Number 3, nanotechnology may introduce new efficiencies and paradigms which may make some natural resources and current practices uncompetitive and obsolete. Number 4, it may be complicated to detect its presence unless one has specialist tools of nanotechnology.